Welcome, it's January 21st, 2025, a day which some would describe as colder than a witch's cauldron on a winter's night. And you might describe the air was like a knife slicing through layers of clothing. It's so cold it feels like the world's been put on ice. The kind of cold that steals your breath away. Frozen solid like the Arctic's doorstep. Colder than the dark side of the moon. A bone-chilling, soul-numbing frost. The frost bites harder than a wolf in a snowstorm. Colder than a politician's handshake. The cold wrapped around me like a glacier's embrace. These are just some of the words that many people will use to describe the temperature, at least at this time of the year, the cold. We could be making this video in the summertime, and it could be the extreme heat, so the other way around. So right now in North America, I'm here in Cookeville, Tennessee, in the central time zone in the United States, where the temperature is 21 degrees and falling rapidly. It's expected to get down to 1 degree Fahrenheit overnight. So that's pretty cold. I also find it interesting that it's also a cold day in hell. In Norway, Norway to be exact, it's 32 degrees Fahrenheit. So they're expecting snow showers in hell. So that's just wonderful. I hope that the devil has a pair of snow skis and maybe some ice skates. That will be very interesting, right? So how do we measure temperature? That's always very important, especially in the science of chemistry. It's very important to know because temperature, as we add more temperature, that makes reactions generally go a little bit faster. And if we lower the temperature, reactions go much slower, right? So it's very important in chemistry, and it's very important overall, even in meteorology and other areas. It's very important to know exactly how cold it is or how hot it is, what exactly a temperature, because that's a unit of energy, right? So how's temperature measured? The first actual temperature scale was developed by this guy, Daniel Gabriel Fahrenheit. He was a Polish scientist and instrument maker, so he actually lived in Danzig, Poland. Now I think that city's known as Gdansk. And so he actually invented the mercury glass thermometer. Or at least he was credited for inventing that thermometer. And so I guess if he invented the thermometer, he needed a scale. So he developed a temperature scale that was based on the freezing temperature of brine. And so brine is a mixture of water, ice, and ammonium chloride as the solute that he used. And he defined that as the 0 degree Fahrenheit point. And at the high point was roughly the temperature of the human body, which we now know to be roughly around 98.6 degrees Fahrenheit, although that temperature we've also found to vary a little bit. It's very close to about 100 degrees Fahrenheit, so it's pretty close on there, right? One interesting thing about that, the Celsius scale, is based on the freezing temperature of water at 0 degrees Celsius. Now that would be pure water at atmospheric pressure. And what's interesting about this is right here between the difference between Fahrenheit and Celsius is the colligative properties, one of the colligative properties of water, that is freezing point depression. So the reason why the Fahrenheit scale is at a lower point, and so 0 degrees Fahrenheit is lower than 0 degrees Celsius, is because when you add solute, ammonium chloride in this case, you're lowering the freezing point of water, so hence the difference of 32 degrees, right? So that's an interesting observation that we can point to the difference in temperature scales. So the one key advantage to Fahrenheit, now this is not commonly used in most of the world, but in the United States and I think Liberia and I think maybe a couple islands out in the Pacific and maybe the Caribbean commonly use Fahrenheit. The advantage here is it's kind of based on human average temperatures. So humans kind of like the room to be about 72 or 75 degrees Fahrenheit. And as things get hotter into the 80s, the 90s, we get used to a nice temperature range as low as like 32. That gets pretty cold, but again, it's still temperatures that humans can kind of exist at, right? So that range is based on the human experience, right? Now, a couple years later, 1742 to be exact, Anders Celsius, he was a Swedish astronomer, he developed a scale which bears his name. So here's Anders Celsius. Now this is also called the centigrade scale. Centi coming from the Latin word centum, which means 100. And so again, it's a scale of 0 to 100. It's based on the temperature that water boils at, and we're talking pure water at 0 degrees Celsius, and water boils at 100 degrees Celsius. On the Fahrenheit scale, again, 1 degree Celsius and 1 degree Fahrenheit don't exactly match up. So the water boils at 100 degrees Celsius, that's 212 degrees Fahrenheit, so it's much higher, right? So again, here we're talking about different degrees, and 1 degree is a different amount of temperature, a different amount of heat energy in Celsius and Fahrenheit, right? Hence why we kind of have to develop an absolute temperature scale, which we'll talk about a little bit later, right? So to convert from Fahrenheit to Celsius, here's the equation. You take the degrees Fahrenheit, subtract 32, and multiply by 5/9. And so if we take the temperature in Cookeville here today, 21 degrees Fahrenheit, we can take 21 minus 32, multiply by 5/9, and on the Celsius scale, it's minus 6.11 degrees Celsius. That's how we can say that our temperature is sub-zero, because we're below 0 degrees Celsius and below the freezing point of water. Now we can convert Celsius back to Fahrenheit by reversing this equation. So we take 9/5 times Celsius plus 32, right? Notice I did not put parentheses on the C plus 32. So we take 9/5 times Celsius, then we add the 32, and then we get 21 degrees Fahrenheit. So we can go both ways, right? So again, because our units, our degrees are not equivalent, we need another temperature scale. We need an absolute temperature scale. And so in 1848, a few years after Anders Celsius gave us his Celsius scale, William Thomson was also the first Baron Kelvin. He was a British scientist, and he developed what is now known as the Kelvin scale. Of course, he's known today simply as Lord Kelvin. And his burial is actually in the cathedral in London, England. You can actually visit that, and you'll see on the floor they've got his gravestone right there. So that's kind of cool. And so he's been immortalized in the annals of science. And so in 1848, he published this paper right here, which is on absolute thermometric scale, founded on Carnot's theory of the motive power of heat, and calculated from Regnault's observations. And so the importance here is this proposed that each unit of temperature would give the same mechanical effect throughout the scale. So 1 Kelvin, whether it's at 0, 100, 200, 300, etc., 1 Kelvin is always the same, right? And so we defined absolute zero, and so you can't get colder than absolute zero. Absolute zero is as cold as you can get. There are no negative temperatures, right? And what happens at absolute zero? That's the point where there's actually no molecular motion. All motion is frozen, right? So there's no Brownian motion, there's no wiggling or anything like that. Everything is frozen solid, right? And so that's why you can't get any colder than that, right? So that's kind of important there. And so we added the Kelvin as the standard SI unit of measurement. So this is the international system. This is what science uses. This was done in 1954. We defined 273.16 Kelvin as the triple point of water. That's actually very close to the freezing point, which is 0 degrees Celsius. Now, minus 273.15 degrees Celsius is absolute zero, right? So 273.15 Kelvin is the temperature at which water freezes at. And the triple point is based on not only the temperature at which water freezes, that's actually the temperature based on, you can actually get frozen, liquid, and solid all at the same time based on certain pressure conditions as well, right? Or standard pressure conditions. So we kind of define that, but today we actually define Kelvin. We've redefined this in 2019, and we've redefined this in terms of energy because, of course, temperature is a unit of measurement of energy, of heat energy. And so we define the Kelvin in terms of the Boltzmann constant, which is 1.380649 times 10 to the minus 23 joules per Kelvin. So joule is the SI unit of energy, and Kelvin being the SI unit of temperature. So we can say that 1 Kelvin corresponds to a thermal energy of exactly 1.380649 times 10 to the minus 23rd joules. And so that's based on Boltzmann's constant, right? So that's kind of a nice thing. And so the easiest way to convert Celsius to Kelvin, if the temperature today in Cookeville is minus 6.11 degrees Celsius, we just add 273.15 Kelvin to that. And so our temperature today is 267.039 Kelvin. One thing you'll also notice here is Kelvin has no degrees. That's because Kelvin, being an absolute unit of temperature, is the unit. It's not degrees of a unit, it is the unit. So 1 Kelvin, or 267.039 Kelvin, are the actual units of temperature or heat energy, right? Both Celsius and Fahrenheit, we will refer to degrees Celsius or degrees Fahrenheit because they will be degrees of temperature. And again, each degree is slightly different. It's not a specified amount of heat, right? We can also convert Fahrenheit to Kelvin, but really the easiest way to do this is to convert Fahrenheit to Celsius first and convert Celsius to Kelvin, right? So here we have F minus 32 times 5/9. Then we do the Celsius to Kelvin conversion by adding 273.15. One thing you'll also notice is that 1 Kelvin is equal to a degree Celsius. So they are the same, but 1 degree Fahrenheit is not equal to 1 Kelvin, right? So they're a little bit different, right? So Celsius, Kelvin, very similar. Fahrenheit, a little bit different. And that brings us to the fourth temperature scale. That's the Rankine scale, right? The Rankine scale was proposed by a Scottish engineer and physicist, William John McLaurin Rankine. He was at the University of Glasgow, and he proposed the Rankine scale in 1859. And so what's unique about the Rankine scale, there's William John McLaurin Rankine. And so this is actually commonly used in engineering systems, especially here in the United States, where they're doing a lot of heat computations that use degrees Fahrenheit. So instead of having to convert Fahrenheit to Celsius first, then convert Celsius to Kelvin, they just convert Fahrenheit directly to Rankine, and so that is pretty common. So Rankine is also an absolute temperature scale. 0 degrees Rankine is equal to 0 Kelvin. Again, you'll notice we do use degrees on Rankine, even though it is absolute, because it's derived from Kelvin. It's derived based on that. Absolute zero is our absolute, and Kelvin defines the basic absolute units of temperature, and Rankine is a unit of temperature measurement based off of that, right? And so to convert 0 degrees Rankine from Fahrenheit to Celsius, all we have to do is really add 459.67, which minus 459.67 degrees Fahrenheit is equal to 0 degrees Rankine, right? So all we do is just add that. So 21 degrees Fahrenheit, we just take 21 plus 459.67. We get a temperature of 480.67 degrees Rankine, right? And so that is our, that's the temperature. And so hopefully if you think in terms of absolute temperature, maybe you'll think that it's not quite as cold as it can be, because we're actually quite warm even at 21 degrees Fahrenheit or minus 6.11 degrees Celsius. It is actually still quite warm for human existence, but it is still pretty darn cold out there. So I hope you stay warm, and thank you for watching. If you like this video, hit the thumbs up sign on there. You can send a comment, and go ahead and subscribe to this channel right below, and hit the little bell icon. That way you'll be notified of stuff. So thank you for watching.